Hello, everyone. I am Miao, a PhD candidate from the University of Western Australia. Our presented paper is Object to Scene, Learning to Transfer Object Knowledge to Indoor Scene Recognition. Indoor scene recognition aims to recognize indoor scenes from images or videos. It can improve the semantic understanding ability of robots, and enable robots to perform more complex tasks in natural environments. Many years ago, most methods used handcrafted features and codebook for scene recognition. In recent years, deep learning-based methods have brought significant progress. At present, most deep learning-based methods for scene recognition focus on exploring rich scene representation features using multi-scale and multimodal feature extraction methods. For multi-scale scene representation, image or feature pyramid, context and patch features could be used. An example of multi-scale methods is shown in the bottom left figure. It uses images at multi-resolution to extract multi-scale features for scene representation. For multimodal scene representation, object existence feature that uses a one-hot vector to represent whether each category of object exists, or depth feature that is extracted from RGBD images could be used. An example of multimodal methods is shown in the bottom right figure. It uses segmentation networks or detection networks to find the existence of each object in the predefined collection of categories. We can observe from the figures that current work mainly focuses on rich image feature representation, rather than object feature representation and object relations learning. The motivation of this work is simple. First, indoor scenes consist of various classes of objects. As shown in the figure below, we use the segmentation model that pre-trained on ADA20K to compute the occurrence probability distribution of objects and object pairs in the places 365-7 classes dataset. It can be observed from the figure below that different scenes have different common objects. Moreover, the co-occurrence probability of coexisting objects varies significantly from bedroom to other scenes. In this figure, we only show the occurrence probability distribution of single objects and object pairs, and it is quite difficult to compute the occurrence probability distribution of multiple objects explicitly, such as the co-occurrence of 150 categories of objects. Therefore, extracting object features and computing object relations hiddenly are reasonable to handle indoor scene recognition problems. Secondly, most current methods focus on rich feature representation, and few of them explored how to construct object features and relations for scene recognition. Therefore, we proposed Object to Scene, which enables using object features and relations for indoor scene representation and recognition. Our method divides the indoor scene recognition problem into object feature extraction, object relation feature computation, and feature vector classification. OTS first uses a segmentation network to compute backbone features and masks. Then, the proposed object feature aggregation module is used to compute object features. After that, the proposed object attention module computes object relation features according to the object features, and the proposed global relation aggregation module is used to aggregate object features and object relation features into a scene representation feature vector. Finally, the recognition module is used for scene recognition. The proposed object feature aggregation module is used to compute object features based on the binary object mask, segmentation probability map, and feature embeddings as shown in the figure below. The binary object mask first filters out regions that out of the object area. Then, according to the segmentation probability and feature embedding of each position, the weighted average method is used to compute the feature embedding of each category of object. Finally, feature embeddings of different objects are concatenated to form the object features of the image. The proposed object attention module consists of cascaded object attention blocks as shown in the right figure. Compared with other attention blocks such as non-local block and self-attention block, the proposed object attention block has many advantages. First, as shown in the table of computational cost, the object attention block is the most efficient one compared with self-attention and non-local. This is mainly because it concatenates the object features, V, and object relation features, R, separately as the output instead of adding the input features and object relation features as the output. Therefore, object attention block does not need any extra heavy convolution kernels to convert the channel number of object relation features from 512 and 1024, which is the channel number of the input features. Computing query features, Q, and key features, K based on the value feature, V, also makes our object attention block more efficient because the channel number of V is half as that of the input features. Secondly, the proposed object attention block is flexible compared with non-local block and self-attention block. It has a variable, alpha, to control the total computational cost and output channel number. When alpha is set to larger than 1 or smaller than 1, the channel number of Q, K, V, and output features will be changed accordingly. However, self-attention block and non-local block cannot change the output channel number. Therefore, the proposed object attention block is more flexible and is easier to be embedded in different models. Thirdly, object attention block is more effective in indoor scene recognition. As shown in the table of recognition accuracy, object attention block achieves higher accuracy with lower computational cost compared with non-local and self-attention, and an efficient version, S, of object attention block only has 70.5 million flops. The proposed global relation aggregation module mainly aims to aggregate the object features and object relation features together to generate the feature vector for indoor scene recognition. It consists of a strip depth-wise convolution to aggregate the features of all objects at each channel, separately, and a point-wise convolution to aggregate the features at different channels. The experiment results show that the proposed global relation aggregation module has a good trade-off between efficiency and effectiveness. It has the best accuracy compared with the fully connected layer and pooling layer with only 2.3 million flops. We first evaluate the proposed OTS on 2 benchmark datasets, and it can be observed from the table that OTS outperforms previous benchmarks by more than 2%. We then ran ablation studies to analyze the performance of each module. As shown in the left table, adding object feature aggregation module reduces the accuracy of the model because ResNet 50 uses the features of CAN5 layer that has 2048 channels, but object feature aggregation module extract features from CAN4 layer that has 1024 channels. What is more, object attention module and global relation aggregation module significantly improve the performance of object to scene, which shows the effectiveness of object to scene in learning object relations. In addition, we verify the generalization ability of object to scene by training the model using Places 365-7 classes and evaluating the model on Sun RGBD. The results show that object to scene still has the best performance compared with previous methods. We use the proposed OTS in an office environment to demonstrate its ability in real-world scenarios. It is noteworthy that the video is playing twice as fast. It can be seen from the video that the proposed OTS performs stable in most scenes. In conclusion, we propose a novel framework object to scene that enables using object features and relations for indoor scene representation and recognition. We also propose a novel object attention module, which has fewer parameters and lower flops compared with self-attention and non-local, to learn the relations between objects. The results show that our OTS has higher recognition accuracy compared with previous methods. Thank you. Our code can be found at GitHub if you are interested in our work.